Yeah, last time we were talking about the history of mathematical logic and what it's about. In the There was some email discussion afterwards with some people. There were several questions that came up. I thought I should share that. So one was a historical remark. Uh, I think it was Purandar who said, yeah, about I said von Neumann heard about Gödel's theorem and Gödel's coding, and he was inspired to think of the von Neumann architecture. And so Purandar asked because you know, actually it was Turing machines that led to von Neumann architecture. So, but von Neumann in a lecture actually mentions this, that it was Gödel numbering, Gödel coding that gave him the idea. But of course, with Turing machines, that was almost like a direct map to build architecture. But that came later. Initially, this is what got him thinking, and then he had a horrendous idea. It was a very difficult thing, very difficult to implement in hardware. But Turing machines came and simplified that whole thing. So that is one. Another.
Jan, can I stop you?
Yeah, please, yeah.
So there are people saying on the chat that some people are waiting to let in.
Okay. What I'll do is, Vikram, shall I make you host? I don't know who was talking
sure,
right now.
Yes.
Who was
talking? I'm Vikram. Yeah.
Yeah, sure, Vikram. What I'll do is I'll make you host. Yeah, I think somebody else will have to be host. I think from now on to. Otherwise, this is not going to work that easily. Yeah, it keeps happening. This is painful. I should have found some way of doing these things. I'm not used to all this. Yeah. You can all see what I'm doing, right? See, it's already gone. It keeps moving while I'm doing. Okay. Vikram, I hope it's okay.
Yes. Yeah. Now I can.
Yeah, thank you. Sorry about all this. I should have thought about all this earlier. Okay, so there was another point which I wanted to mention, and I think it's also very important. Shankar brought it up, and I was presenting mathematical logic principally as doing mathematics of logic, reasoning about logic, right? Saying, like I was talking about Gödel's theorem, and so that if you have arithmetic, then there are always some sentences that are not that you cannot neither prove nor disprove. So these are mathematical statements about logic. Well, another way of looking at mathematical logic is approaching mathematical structures, studying them by means of logic, right? Using logic to study mathematical structures. And so, shouldn't that be the thing? That's what Shankar asked, and it's a very important view. And in fact, what is called model theory is principally that. Principally, model theory is the study of mathematical structures via logic, and that's what we're going to do in much of this course as well. But we will use that as a means to actually get to what we call these meta-mathematical statements about mathematics, about mathematical structures, about logic itself using mathematical terms. So both are going to be very important viewpoints, but of course I was pointing out a historical development. In terms of historical development, that point with Gödel and the Hilbert program changed many things in the way logic is done. The way, it's almost like a dividing line. The way logic was done earlier and the way logic was done later. The earlier part, and quite a lot of it you can place within mathematics, like like what I would call the algebraization of geometry. You can say the logicization of analysis, logicization of certain fields of mathematics. It's more of that. So these are historical remarks, but I think they're important to mention. Okay, so a lot of history. Now let's get to the real business, so to speak, right? There are some remarks on chat. Notice that it's quite painful for me to see from on chat here, since I'm not, like last time I was doing it on my laptop, whereas now I'm using this room, right, a classroom. So it's better, don't write on chat. If you have anything to say, please switch on your audio and talk. It's much easier for me, right? Yeah, thank you. And as I requested, there is some more possibility to see on the screen if more people turn on their videos. Yeah. Okay. Now, we're going to start with talking about the language of logic, and I have in fact written languages of logic, and I want to actually emphasize this point, and that's going to be the kind of important take-home thing. I mean, we tend to think of logic as a language, even when you think of it as one language, the logical language. And I think unlearning that is also very important. But for that, okay, here's a little game. Okay, this is a game that we all play as children, right? Okay, first the children's game, and then we can grow up a bit. Okay, so the children's game is this: I've thought of a number. Try to find out what that number is. Yeah, quickly. You have to ask me questions to find out what that number is. Who's going to go? Megha? You can ask me any questions too.
Is it a prime?
Okay, so she's assuming that the only questions allowed are yes, no questions, right? Otherwise, you could have asked me what is that number and I would have told you. But anyway, since you are making it harder on yourself, okay. No.
Is it a perfect square?
No. What else?
Is there a unique property about the number that you can tell me?
Well, it's got lots of unique properties, but I don't know. I mean, well, it has unique properties. But in fact, this is a very complicated question, and I don't know how to answer it really. Okay, it's good, but go on. Yeah. What else can you ask me?
How many digits are there in the number?
Oh, you mean okay? Yeah. So, how many? I'm afraid I can't answer that.
Okay.
What does that tell you?
It's a real number.
Okay. Yeah, I never said it's an integer, did I? Okay. So you know how this game goes, right? And now, if it's a real number, you're in serious trouble, right? What kind of questions would you ask?
Sir, is the number less than 100?
It is, yes. Who's speaking? Megha. No?
Ritu Parna.
Okay, yeah. Can you switch on your video so that let's just continue the game? Yeah.
Yes, sir, I have switched on.
Yeah, okay. It's somewhere, I suppose. Yeah. Okay.
Can we write the number as a root of an equation, of a polynomial equation?
Okay. No, I'm afraid not.
And it's not an algebraic number?
Yeah, that was the purport of the answer, yeah.
Is it E?
Now you're beginning to guess, and these are good guesses. No, it's not, but yeah.
Is it pi?
Yes, it is, yeah. So it is indeed pi. And okay, so the thing is this, look at this game, what's going on. If it's the usual, game with integers from 1 to 100 or something like that. Typically you can use binary search and find out or whatever. But now the moment it's a real number, you have to think of all sorts of things, right? Okay, now it's going to get more interesting now. I have thought of a subset of natural numbers. Okay, Kamalika, can you try to find out what that subset is? What will you ask?
Is it finite?
Chinmay, yeah?
Is it finite?
Yes, it is. Anybody else? Anyone can. Just continue. I mean, okay, it's a finite set. Now what will you ask next?
What is the largest element?
What is the largest element? 72. Where are you going to go with it?
Is it all the divisors, all the positive divisors of 72?
Good question. Well, no, but okay, I'm not going to go down this road. Okay, so you see that the kind of questions that you ask are different, right? Okay, now just one more, and I'm not going to go on with this. Okay, I've thought of a finite graph. Okay, yeah, you want to find out that graph. Gayatri, any question? What will you ask? I've thought of a finite graph. Are you on mute? I can't hear you. Sorry, I can't hear you. Some problem with your audio, I think. Siddharth?
Sir, what is its adjacency matrix?
What is its adjacency matrix? A great question. So if I give you that, you've got the graph, right? Now let's stick to yes/no questions, okay?
Okay.
So what
is it connected?
This is the point, right? So one important thing is that why are we sticking to yes/no questions? Because I want to describe the graph or the real number or that set, whatever, by its properties, right? And properties we think of as being true or false, right? So that's what is the business of this yes/no questions, right? So is it connected? Yes, it is. Okay, a finite connected graph.
Is it a tree?
What is the question?
Is it a tree?
No, it's not. So now the questions that you are asking me are all about the entire graph. Now, what kind of questions could you ask about this? You want to look at the structure of the graph somehow, yeah?
Sir, if we consider it as a lattice diagram, because it's a finite graph, does it have any infimum or supremum?
To consider, I don't know. Who's asking this?
Yes, sir, I'm Ogniva from Kolkata. Hello.
Okay, where are you? I'm looking for you somewhere.
Okay, sorry.
Okay, speak up. It says so. You should speak up. Yeah.
Yeah.
Okay. I don't know how to answer this question. Can you go into the structure of the graph? We know it's a finite graph. What sort of things would help you to describe? So what are we really talking about? I want to describe a finite graph up to isomorphism, right? I mean, that is really what we have to think about, right? If that is so, what is the description that we want? What else can you look for? Anybody?
The number of vertices.
Yeah, okay, you want to get something on the cardinality. Well, I was saying yes, no, but okay, now I'll have a count question here. So, say 5. Yeah, 5 vertices.
Degree of the vertex.
Degree of which vertex?
Yes. All the vertex have same degree.
No.
So the deal was about yes/no questions, right?
That's true, but since somebody asked and okay, so now I'm saying that okay, so we had yes no questions, now there is a count question, right? There is a cardinality question, okay? And this is really what the theme of this whole business is about, that we want to talk about a particular language in which we talk about these structures, right? The particular structures of interest being, like we said, graphs, we said real numbers, sets of numbers, whatever, right? So, okay, so I mean, I hope you get the idea. We can play this game. It's a nice game. We can spend a lot of time doing that. And I think of a vector space. Try to find that vector space. What questions would you ask, right? So I can play this game with pretty much any structure. I mean, if I say vector space, what kind of questions you would ask, right? I'm right now, for the purpose of our discussion, think of that. Basically, those questions have to be articulated in some language, right? Now, what are the primitives of that language? The moment I said graph, Siddharth was asking, is it connected, right? Connectedness is a property that you want to describe. The cardinality of the graph is not a yes-no property, but it's of something of interest. It's a count property, right? Something which gives you natural numbers. But maybe, for instance, if in the case of a vector space, what question would you ask? How would you think of that?
The dimensions and the basis of the vector space.
The dimension, what is its dimension? That's a good question. Okay, that's again not a yes-no property, but it's a count, right? And if it's a finite dimensional one, yeah, okay. Well, there are enough computer scientists around. Instead, suppose I say, I've thought of a database. What question would you ask? Who says you must think about only these mathematical structures that you learn in some math course? Huh? I've thought of a database. What kind of questions would you ask to find out what the database is? How do you even begin? And thereby, hangs a tail, as they say. There are issues here. Okay, so this.
Whether that database have the label set or what?
Can you just say who it is again? Since I'm not seeing people, I have to know. Yeah, who's asking?
Anand.
Okay.
Like you consider as a data set, so I'm asking that whether that data set considered the label set or unlabeled set.
Or in general, when you say database, you are talking about labeled objects. Yes. Yeah.
Okay.
No, I said database. Right? Database has some schema, some structure. There is a whole lot. I mean, you think of it as a set of tuples, right? The main point is that you have to describe the entire tuples, or is there some simple description from which the whole database can be generated? So these are the questions, right? So, okay, so all this is a lot of fuss to say the main point I wanted to say, namely that you have, we use these logical languages, right, so when we were talking about graphs, certain terminology was natural, right? Like in the case of connectedness or whatever. In the case of numbers or sets of numbers, some other terminology was natural. So you might think of this as the kind of primitives of the logic that we are using. This is really the point I want to make. So if we now want to design a logic, design a language, right, in which we want to talk about, let's not worry so much about databases because it's not clear what we are going to say, right? So let's say at least that we are going to talk about mathematical structures, right? By mathematical structures, graphs are okay, vector spaces are okay. I don't know, what are your favorite mathematical structures, whatever your favorite mathematical structures. So let's stick to mathematical structures for now. And I want a language to describe, so the language is to describe mathematical structures. what would be the kind of primitives of such a language? Basically, the language in which mathematics textbooks will be written. This is what I want, right? So pretty much I want some languages, and I want the languages to be minimal. This is the other thing, right? I want the language to be minimal. With as few primitives as possible. I want to describe whatever is the language of mathematical structures of interest. And so let's start with something which is probably the simplest that we all start with, namely arithmetic, because that's what we start with. In mathematics means arithmetic, right? In school, that's how we all learn. So arithmetic. So no real numbers. We're only talking about integers, not even negative integers, whole numbers, 0, 1, 2, 3, natural numbers, right? Natural numbers include 0 for me, please. School textbooks make a fuss about all this nonsense, but to me, natural numbers is 0, 1, 2, 3. Now, if you want to talk about a language for arithmetic, what are the kind of things that it should have? Primitives. She asked me when I said number, first question Megha asked was, is it a prime, right? So, prime is something that she wanted. What are the other questions that, but now prime is what? You say a number is prime, right? So, you want to say n is prime or x is prime or whatever. This is a sentence we want. What other kind of primitives you would like? Yeah. There was some question about is it less than 100, right? So surely you want to talk about ordering. You want to say m less than n. Okay. What else? Yes, Gayatri, I see you saying something, but I can't hear you. Oh, your audio is a problem, is it? Okay. Yeah.
Operations.
Operations. Yeah.
Like addition, subtraction.
Addition, subtraction, so functions. So you might want to actually write things like why not? Yeah. And so addition, multiplication, subtraction, of course. Yeah. So you have some functions in mind. Okay. Maybe exponentiation as well. I don't know what you use, so let me use this. Okay. So you have some functions, and I've written that equation out there. So one thing that you have is equality. You also have inequality. We already had greater than, less than or equal to, greater than or equal to. Comparison, right? So the moment you've got comparison, equality, these arithmetical functions, you already have a very good language, right? In fact, this little language that we have got here takes you all the way through primary school and middle school, right? We have already arrived at within like 2 minutes into middle school. Not much further, okay, but at least this much. And already this has brought us to integers. And in fact, what about this particular equation? Does it have a solution in integers?
Yes. Yes.
Yes, it has. Okay, so we also have notions like this particular equation has a solution or does not have a solution, all this. Prime was one thing slightly different from this. This said n is prime. Maybe we might also have, since we have this, something like m divides n, right? Or m does not divide n. Okay. Can you tell me some theorem with just these kind of things? Maybe some statement? Not theorem. I mean, I'm just saying some statement which is true or false, right? When I say this has a solution, what is it that I have in mind? I am saying there is some x, there is some y such that this is true, right? And we are used to writing statements like this, right? And this is we usually don't write the quantifiers, right, in school when we learn, right? But typically when we write something like solve, right, solve 5x plus 4y equals 25, what we mean is that there is an x and there is a y such that 5x plus 4y is 25. And the world in which you are living at that time is integers, so you are supposed to plug in integers and solve, right? At some point you get a bit of a shock when you realize that there are some things that I can write for where integers will not suffice at all. But let's worry about that later. But my point right now is, okay, so if we want to do the language of arithmetic, what will be a minimal set of primitives with which you can write all these? This is the question, right? So what are the things that we will keep and what are the things that we will throw? So let's see.
So we don't need divide.
We don't need divide, okay. Why don't we need m divides n?
Because we can divide it in terms of other primitives like equal to and division.
Okay.
Multiplication.
So I can define this by saying what? Yeah. M divides n, equivalently I write in what way?
Like if there exists the integer k,
There exists k such that
k into m is equal to n.
n equals k times n. If I have times, okay, so there is already one argument, and this argument that was given, what is it about? Is it about numbers at all?
Sir, so we are needing the there exists thing, right? So that is a quantifier, right?
Yes, yes. So you are using the quantifier, right, to eliminate. So the quantifier there exists is here is, so in this particular assertion here, there exists is used to define, what was that? Divides from multiplication, right? This is really what you had in mind, right? Yeah, so my point is that here you are reasoning about the language, right? You are saying in the language, if I am going to have quantifier, if I am going to have multiplication and I am going to have equality, I don't need to have the divides as one of my primitives. It is in this sense that I am saying we want to be minimal, right? So, well, people say various things, but where did 5, 4 and 25 and all come? I need, so what about, so what else do I need in my language? What about numbers, right? I mean, I do, huh? Sorry? Constants, okay. Constants is the name, but the point is that I have numbers in mind, right? And I have numbers like 5, 4, etc., specific things in mind, right? I did not write what? Give me some. Oh, no, I need some. I didn't, huh? If I had, you could say, it's some weird creature that I'm talking about. I have numbers in mind, right? You read it with numbers in mind, so let's say numbers. Why should we call it by some other name then? So, what we have in our language are numbers, we have equality. What else do we have? We have plus and times. Are you going to eliminate times as well? What about minus? If I have plus, do I need minus?
No, we don't.
No, we don't. Why?
No, we don't.
Who's saying this?
It's the same way as plus.
Okay. Yeah, it's the same way, right? I mean, it's the same sort of nonsense, right? So, of course, and this is something we do, I hope we do learn in primary school. One of the things is that addition and relation between addition and subtraction and multiplication and division, that, okay, fine. So, but then what about addition and multiplication? Maybe we can write similarly multiplication in terms of addition. Yeah, why not?
So if we are using integers in this case, so
Yeah.
our multiplication will basically be repeated additions.
I know. So how will you write it? I'm asking you how you will write it. Yeah, who is speaking?
So Shudabna.
Okay. Yeah. So I hope I can find you.
Yeah, but how will you multiply two negative numbers?
Well, I'm only talking about natural numbers right now.
Yeah,
So
yeah.
I'm only
Basically,
talking about natural
we
numbers.
are actually talking about natural numbers, including 0 here.
So Lagna, can you tell me how to write multiplication as using repeated addition?
Sir, in that case, if we have any statement like if we are multiplying k with x, we will write that there exists an
Wait. K times x equals.
We will write x plus x up to k times.
Up to, but I don't know how. Oh, you are saying I need some primitive like up to, right? Okay, so that means
Yes.
x plus x plus x plus up to k time, right? Okay, but what is this? Now you are bringing in something else. It's not plus times and so on. You are bringing 3 dots. 3 dots is part of your language, right? And writing up to k times as part of your language. This equation here is very different from this equation here. Yeah, these are very different things. Is it clear? I hope.
So we are actually using addition as a binary operation, right? Like we are taking 2 x's and we are adding that to x. After that, we are adding 1 more x. So in that case, aren't we using the addition operation repeatedly, finitely many times?
In this definition here, yeah, I agree that it is meaningful to you and me. There is no problem. Yes.
So we can define multiplication recursively, right? Like k plus 1 into x is equal to kx plus x.
Equals
Kx plus x.
K times x plus x. Yeah, but what is this? This is not an equation now. What you said, this is not an equation. You said this is a definition. So you are saying there will be two.
We are defining multiplication with using addition.
I agree, but now you are bringing in a new linguistic. As far as language is concerned, you are bringing in a new thing called definitions. Here, when I write equal to, I mean it as an equation. Here, when you write it as an equal to, you mean it as a definition, right? See, I said we have arrived in middle school, and I can already see the confusions of the middle school, right? Middle school mathematics, one of the greatest confusion is this symbol equality, right? I do a lot of work, math for children, right? And I see this with the school children and school teachers. This is a huge mess because equality usually means this for all school children. Unfortunately, there are also equations of this kind. What particular values of x and y for which this holds? Yeah, which ones?
All the real values of
every x and every y, right? So here when I write this, what I mean is for all x, for all y, x plus y equals y plus x. Whereas when I write here 5x plus 4y equals 25, I mean there are some values x and y, and it gets more and more messy. And so part of this is the problem. In our math textbooks, we are used to using equality as we like freely. Some places we mean it in this sense, like what Sulagna was talking about, where we are, come on, why shouldn't I write that curly thing and say up to k times? It makes perfect sense between you and me, right? So one of the aims of designing a logical language is to minimize all this kind of ambiguity. Okay, so one thing that I assure you that you're going to get terribly frustrated by when you learn mathematical logic is the tremendous amount of pedantism and bureaucracy in the way languages are defined. And if you don't get frustrated, something is wrong with you. That means you're not going deeply enough, right? Logicians are extremely pedantic and bureaucratic in the way they define languages, but it is because of this minimalism and not accepting this kind of overloading of symbols of this kind, right? Equality is way too important for understanding mathematics to be sanguine about it, right? It's okay to write your textbooks, write all this kind of stuff, but unfortunately it brings in a whole lot of questions which we want to address directly and answer mathematically. And if you want to answer these questions mathematically, right, there are, like for instance, can multiplication be defined from addition using simply quantifiers and things of this kind, without having new kinds of equality coming in, without these 3 dots coming in, without this extra annotations coming in? Well, if you can, just do it. If you can't, how are you ever going to prove that you cannot, right? So this is it, right? Okay, so we are now going into, when we are doing this exercise, so for arithmetic we have decided we will have these addition, multiplication. What about exponentiation? For now I am going to keep both. I hope Shulagna will not mind, right? Because I don't know how to write this up to k times is okay, but that the most problematic thing for me is those 3 dots. I don't know what to do about those 3 dots, right? One of the most, to me, fascinating things to give a precise meaning in mathematics is this 3 dots, right? We love using that, right? Oh, come on, we do this all the time, right? I mean, 1, 3, 5, 3 dots. Yeah, I mean, we write sequences, we write infinite series, everything. This the moment there is 3 dots with nothing following it, all kinds of signals start popping up in our heads, right? It's a very meaningful thing. But for now, I'm going to ban it because it's difficult to give meaning to, right? Okay, so that's, and why is it difficult? I hope somebody will remind me if I don't discuss it later on, right? But for now, we'll keep it out. Okay, what about exponentiation? M power n. Is there some way by which you can give me a nice description? I think.
We can finally define it recursively.
Yeah, but again we get into definitions. It's the same as 3 dots, right? You're back to 3 dots because with 3 dots, I mean, Sulagna has already given me the formula for writing this, right? I have to just write m times m times m. The moment I have got 3 dots, I can write it like, or you change equality to write, right? You are allowed to write m power n plus 1. Yeah, okay. Yeah, sorry, somebody? I don't want to bother with all that now, so let me put this in. Or what shall I call this? This is for exponentiation. Yeah, okay. So I'll put that in also. Somebody said prime, right? Yeah. We already know how to write m divides n. For prime n, can you give me a definition? We said you're using quantifiers, so use quantifiers and tell me, when is n a prime? Yeah? Was there anything else that I missed? Okay. Yeah, have you
Sir,
figured
we
it out?
need, sir, we need such that. Hello.
What is such that? Yeah, such that is a very useful mathematical thing to have. So we put such that somehow. Yeah, how are we going to use such that? Yeah.
So there exists B and C such that B multiplied by C is equal to A implies that B is equal to A
Very
or
nice,
C is
very
equal to
nice,
1.
right? So what you are saying is that if A times B equals N, this implies, let me use this, implies what? Yeah,
A is equal to N or A is equal to 1.
A equal to 1 or A equal to N. Huh? Sorry?
So we needed or as well.
Yeah, but what happened to B? You said A equal to 1 or A equal to N? What was that?
I think it suffices, right? I mean,
Okay. Yeah, I mean, it's a bit funny to have A and B on the left hand side, but only one on the right hand side, right? So that's why I thought you will use the divides, right? So why not? Oh, I'm using-
no, I mean when we are saying A into B is equal to N, then putting conditions on A inherently put conditions on B, right?
Of course,
So when we are saying A is equal to,
that's true. But this is the joy of using definitions that somebody has already done, right? It just says Ghosh. What is your name? Ghosh is.
Yes, sir.
What's your name?
Swapnil.
Swapnil Ghosh. Yeah, Swapnil. Yeah. He has already defined M divides N for us. So I might as well say if A divides N, then I can eliminate B, right? If A divides N, then A equals 1 or A equals N, right?
yes, sir, yeah.
And now, but what is the such that you wanted? Which A is this? You said if there exists an A, but yeah, is it for some particular A? But why should, yeah?
No, I was defining from the, so the implication was I mean, I started from the right.
So this is clear.
That's why
This is very clear. So, but which particular A are we talking about?
Sir, there's a problem with this statement.
Who's saying this?
Siddharth.
Okay, yeah, go on.
Sir, according to this definition, n equal to 1 will also be a prime.
Yeah.
Yeah.
Yeah. So.
Yeah. Sir, like.
No, that's why. No, wait. We haven't said anything about A. He said, Siddharth, you can object only after he says which A it is, right? Maybe the A that he has in mind is not 1 at all, right? A is just free here. It doesn't mean anything. If he had said for all A, this is the case, then Siddharth, you should definitely object, right? For all A, if A divides N, and if this is what he had said, you should object. But he didn't say that. I hope he was saying that, but and then we can fix it. So Siddharth, say, what should I do? For all A, what should I say?
So there exists A not equal to 1 such that A divides N implies that A is equal to N.
Okay. There exists A such that A not equal to 1, and it's getting more complicated, right? I would leave it at this, but then fix it for all A. When we usually say this, what do you mean, right? What about A greater than 1, right? What's wrong with something like this? Yeah, I mean, we usually write such things, no? And that's really what he had in mind when he said, right?
Actually, we are assuming that A is strictly greater than 1.
Yeah.
And after that, we are implying that A is n or A is equals to 1. So our implication might give some contradictory result over that.
Okay.
No, I said implies that A is equal to N only.
So who's that? Who said this?
Sir, forward. Yeah, me, sir, Ognivo, yeah.
Okay, yeah, fine, yeah. Okay, Yeah, so, and now, she's pointing out this interesting thing, because I put for all a greater than 1, and then how can you write a equal to 1 out here, right?
No, we don't need that one. Just a
We
equal
don't
to
need.
n will suffice.
We'll do this, okay? Okay. Does this give you a prime? Is everybody happy with this? Shivani? Yeah? Siddharth is extremely unhappy with this whole business.
Sir,
Yeah. What's the
what
problem?
if n is equal to 1?
Huh?
What if n is equal to 1?
What if n is equal to 1? Okay, so what about prime n? Means n is not equal to 1 and all this. Okay, so this is what is called bugwise refinement, which Dijkstra used to laugh at, and surely this is not. You must look for the most economical way of saying these things, right? And so we want to say it. We want to say it as minimally as possible, as economically as possible, and as elegantly as possible, right? Okay, there are going to be lots and lots of exercises. Don't worry, right? For you to do. Now,
I have a question.
sorry.
So this is Ananya.
Yeah.
So, like over here, what we did was define what prime n is. So we are basically defining something. And a little while ago, you said that multiplication and exponentiation would be a part
Good.
of this setup. How
Okay.
do we decide
Okay.
when to define?
Yeah. So I have no business writing an equality here. This is not an equation. What I was objecting to is this writing it as an equation here, right? There are two things here, and I want to. Here, I am just saying this entire thing is a shorthand for writing prime n. Okay. Whenever you hear prime n, you can always substitute it by this. If we fix it nicely and make it nice and so on, we can. Again, I don't want to give any particular definitions of prime here. Huh? You are free to write your definitions of prime. What is the project that we are taking up? Not this at all. Whether I should have a primitive called prime in my language, right? All this says, okay, you can write it messily, you can write it in whatever way, but I don't need to have prime as a primitive, right? That's all that is of interest right now for me. Here, I don't know how to do this because this 3 dots bothers me, right? Even though I have written more dots actually. Yeah, oh, okay, one of them is multiplication, yeah, right. So, yeah, that's.
The question is like, when do you decide whether to include more operations, like operators, like
Good.
these 3 dots or implication,
Absolutely.
or like such that.
Absolutely, absolutely. In fact, I don't want to have any of this. I'm just trying to point out that right now we don't need it. So you do it only when you need it, right? Now, how do you decide that you need it, right? Need means what? I can't do without it. That cries for a proof, right? You should be able to say, I cannot write this multiplication in terms of addition. I cannot write exponentiation in terms of multiplication without having this problematic 3 dots. So it's a choice, right? Do you bring in the 3 dots, allow recursive definitions, or throw away recursive definitions, throw away all the 3 dots such that up to times whatever those kind of statements of this kind, but throw in the function itself directly. Right? This is the kind of decision that I am talking about. Is that clear? So for now, I am saying this is what we have. I don't have any more. This, what is called prime, is what logicians like to call a predicate. Right? It's a predicate that is true of a number. Right? Now, okay, but this is still for a particular number. What about a set of numbers? Some set of natural numbers that you know of? Well, the moment I said when I wrote this, for instance, this implicitly describes a set of numbers for me, right? Because it says any n that satisfies this, right? Such that whenever I pick an a, right, and if it divides it, it must be equal to 1 or equal to n or whatever that person said, right? That's true for all a. This actually defines a set of numbers for me, right? I was thinking that people would take more simple examples. What about this? Again, how would you define n is even? Well, somebody already had, you have natural numbers, he has already done the divides for you, why not write 2 divides n? But this seems like a very expensive way of talking about evenness, huh? Because this requires division, which requires multiplication, and we don't know whether I can write multiplication in terms of addition. What about writing even only in terms of addition? I want to say n is even.
If there exists a case such that n is equal to k plus c.
That's it, right? Again, Ananya, I'm not writing an equation. I'm just putting 2 dots here just to write. There exists m such that, yeah. And notice that in whatever I am doing, I'm putting parenthesis wherever I like. Sometimes I put it on this side, sometimes I put it, okay. So that will also will be a little more cautious about it. But yeah, so this says that, okay, since I've got addition, now I can define evenness. And once I've got even, I can define odd, right? I've got even, I've got odd, I can talk about odd primes, I can do more sets, okay? What about relation between numbers? What kind of relations? We already said certain relation, like, what about this? Can I define m less than n? Yeah.
So, can we use a mod function or squared function?
You can use anything you want. What is stopping you from using it? The question is, can you define it with whatever you've got, or you need more machinery, right? But what about m less than n? How will you define that?
Hello.
Okay.
Yeah. So
Yeah.
Greater than 0.
There is a k.
Then we can say n is equals to m plus k.
And is that enough?
K needs to be positive. Positive greater than 0.
Well, positive means what? Greater than 0, but greater than, I don't want to define less than using greater than. Huh? Yeah, it's simpler. I write k not equal to 0. Not equal to 0, right? Yeah. And what about m greater than n? Of course. Come on. Yeah, okay. So this game one can play. It's an interesting game. The idea is somehow to find some minimal vocabulary from which you can generate. Now, what are the things that we have actually used? We have used equality, we have used these functions, and we have used numbers. Now, numbers, do we have to have the whole infinite set of natural numbers with us for writing all these things? Or since we have got some functions, can I use some other functions to define natural numbers? Well, there are various things. Many books would say, well, just use successor, so that use something like 0, successor of 0, and then you get too lazy to write. And so on. So you use a unary function like successor to talk about,
Sir,
to write any numbers.
hello.
Yeah.
Sir, so while talking about even numbers, you said that defining even with respect to divisibility, which depends on which then depends on multiplication. So it is non-economic. So we just did it with addition, right?
That's assuming. Wait. That is assuming that you can't write. Yeah.
But what I want to say is that there existing is itself non-economic, right? Like
absolutely.
Absolutely. So do we compare our choices there also?
I do want to take it up. I agree with you, and I completely agree with you. Who said this?
Yeah, Agniho.
Yeah. Okay. It's also something. Why should we have these quantifiers? There exists. You are objecting to there exists. What about for all? Right? You can object to for all. And I'm just pointing out that these are things that we are using, and we must question every single one of them. right? So I do want to look at things without, like I do want to look at addition without multiplication and exponentiation. I do want to look at a language where you are not even allowed addition. And Agnivo, you should be happy to hear, I do want to look at things without quantifiers, right? Point is, what do you do with these languages? We should be able to prove certain theorems about them, right? That's what we are here for. That's what mathematical logic is about. You should be able to say, I cannot define this in this language without these resources, right? Let's put that word down, because this is going to come lots, because that is a connection between all this stuff and computer science in some way. When I say minimal and economical and so on, I have some, no, what are the logical resources needed, right, to describe a finite graph, a vector space, right, a real number, whatever, right? But the resources that I am counting now is not in the sense of money, right, whatever resources, energy, this thing, but logical resources in terms of the logical machinery involved, right? So this is typically called descriptive complexity, right? The subject is called descriptive complexity because you want to see, to describe a structure, what's the minimal resources that you want. Now, I'm afraid we are not going to get into theorems of descriptive complexity in the course. Maybe one as an instance we'll get to later on, but the name of the game is very, very clear. That's really what we want, right? We want to describe mathematical structures unambiguously, precisely, right? But with as few logical resources as possible. Quantifiers are, point is well taken, right? And we have used and, or, implies, there exists for all, right? So, and you know, what about 0 itself? Can I write 0 somehow? If I write 0 like this, it's very hard to even think of how you would go around writing a description of 0. Let me follow the same language to write. Maybe this will help you think. We are talking about natural numbers.
Hello?
Yeah.
It is a number x such that, for all m,
Yeah.
x plus m is equal to m.
If you have addition, yeah, for all m. Yeah. If you have addition, or if you have, it depends on what you are given, right? We used addition to describe order, right? Comparison. And we are using addition as the primitive for all of these. So it's clear that you can describe order using addition. What about the other way? Can I describe addition using order? Can you give me something of this? Definition of this using something with order? Not clear, huh? I should at least write m plus n equals p. Because all the stuff I am really talking about are predicates, some things that are true or false, whereas this is a function. So order is something that's a predicate, it's true or false. So already there are two kinds of things that you've got on hand, right? Some things that are true or false, some things that are objects, but like functions and so on, which are not really true, false, or anything. So already all this, I hope the project is beginning to make sense to you, right? I mean, we'll write some definitions and proposition lemma type of thing, but the idea of what we are doing and why we are doing should be clear, right? That what we are saying is, for instance, we are able to define order using addition. Question is, can you define addition using order? What's your conjecture? Yeah, let's take a vote. How many people think addition can be defined using order? So all the yeses, please. How many people think no, it cannot be defined? Yeah, put up your hand so I can see. Yeah, you have to vote. Huh? I mean, you can't be silent on these things. Yeah? Chinmay, I saw your hand. For which? For no.
Yes, no.
No. Okay. Kamalika? No. Okay. No. It's good that democratically we can now decide that you know, addition cannot be defined using order, but how do you prove it? How would you prove that? I mean, okay, it's one thing you say. Yeah, on chat there is a lot, but I've told you already the chat is difficult for me to make out. Yeah, so there is a kind of overwhelming no. So as I said, yeah, but that's a democratic decision. Doesn't help mathematically. How would we prove it? Okay, so this is one of the important things that we want to learn from this course, right? We want to discuss definability, right? So this is one of the important things that like I told you, last time I promised you that what you learn from the course is what? Any good courses, a set of questions you should ask, right? One of the very good questions that you learn from a logic course is what is definable and what is not definable. Somebody comes, Akil comes tomorrow and proposes a new logical language. You have to ask, what are the things that are definable in your language, what is not definable in your language, and if he claims something is not definable, can you prove it? Now, those proofs are not easy, right? Definability, showing something is definable is easy. You can write a definition. Showing something is not definable is very hard because you have to have some closure properties, you have to show some interesting things. Hopefully, we'll learn one or two tricks at least on this, right? So, definability of things in terms of each other, definability of a property. Siddharth, when I said graph, is it connected? Now, can connectedness be defined in terms of whatever else I can tell about the graph, right? Now, we hope so, right? But say if there is a property that we cannot define, how will you go around proving that it's not definable? So, the language of arithmetic, we had all this. So, let me throw in all this stuff. So, here is one language of arithmetic that has numbers, addition, multiplication, exponentiation. This is a bunch of functions, and then we had equality, less than. This is some particular kind of true false statements which I called predicates, and then we had some and, or, implies, not. Where did I use not? Did I ever use not? Where did I use not? I happily wrote not equal to 0, right? What does that mean? So I use not. Something like this is the language of arithmetic that we have been talking about, right? It's fine. Let's move on. Now, already there are, yeah.
We are defining here and there exists. So is that for all redundant? Like not like there exists can be negated by saying for all?
Possibly. We'll get to it, right? Let's not worry about it for the moment. I'm just throwing in whatever we were using, right? Yeah. And of course, you want to be minimal, you want to cut down. If one thing can be expressed in terms of another, we can get rid of it. We'll get to it. What I want to point out to you that in this language there are fragments of interest, by which I mean there are sub-languages in some sense, which we have already promised that they are interesting. Like for instance, the same thing with addition, but not multiplication, right? Addition, I don't need order, I said, but I'll throw in order but no addition. For instance, this language. Let me use this. with just order, right? No addition. In which case I can't write many of those things that I was doing, right? Because we don't know whether addition can be defined in terms of, we all decided addition cannot be defined, right? So what can you say in this language that, what can you say in this language that cannot be said in this language, and so on, right? There are lots of fragments of interest with, many different combinations. It's actually, but what is very interesting is that even when we look at these fragments of interest, these things remain the same, right? It's only the vocabulary here about whether I am allowing particular functions or not, particular relations or not, that I am changing. But the basic way I am talking about one particular thing that is of interest is also throwing away quantifiers. This is also talked about. That's also a fragment. So even when we talk about arithmetic, there is not one language of arithmetic. There are many different languages of arithmetic. That is the spirit in which I wrote that plural right in the first time that I wrote, right? So there are interesting languages of arithmetic, and one project that we want to take up is difference in definability between these languages. Okay, so next, what about the language of graphs? What is the sort of statement that you will have? So I want to talk about graphs. Yeah. When I write M, N, etc. so far, what did I have in mind? What was M and N supposed to stand for?
Natural numbers.
Natural numbers. Now when I write M, N or X, Y or whatever, what will I be talking about? In the language?
Vertices or edges.
Vertices, right? Vertices, let's say. If you say X, Y, etc. is talking about vertices, how would you describe edges? You need some relation, right? So let's say that we have a binary relation EXY to say there is this is an ordered pair, so this gives you a directed edge from X to Y, right? Okay. So now, what else will you want in the language? Of course, as I said, you can, name some property. What about that it's connected? Is there something you can say? What does this say? Or maybe what does this say about X? This symbol is what I usually use for not. It is not the case that there is a Y such that
X is an isolate point.
Yeah, right. Or what about EYX? Yeah, well, it doesn't matter. It could still have incoming edges, right? So let me put it this way. Yeah, this says that there is nothing coming into X and nothing going out of X. X is actually sitting isolated. So this is the kind of property that you might say. With just quantifiers, I'm using symbols of this kind for OR. I know we are all used to many of these. My point is that with just this machinery, you can start saying some things. What about connectedness, Siddharth? How would you write?
If there's a sequence of vertices. Sorry. If there is a pair of vertices such that there is a sequence of vertices.
There exists, let me write. Yeah. For every pair of vertices, right?
Yeah.
For every pair of vertices. So let me write it as for all X, for all Y.
There exists a sequence of vertices y1, y2.
I can write there exists here some sequence of vertices, yes.
The sequence be y1, y2 up to yn.
But 3 dots have come.
Okay.
I am very worried about these 3 dots, right? This is a real problem for me. I don't know how to. Okay, we will keep, for now, that's what I said, we'll ban 3 dots, right? Yeah. Why? As I said, thereby hangs a tail, right? But okay, so let's postpone connectedness. Anything else? What's a graph of this kind? What does this say? What does this say about the graph?
Complete graph.
Yeah, complete graph.
Correct graph.
Yeah.
Complete graph.
Complete graph. Yeah. And so you can play around a lot with these things. So the language of graphs is extremely simple, right? You have your x, y to denote vertices. You have a binary relation, and you can say many things. So already it's so simple that we don't have to worry about fragments and so on, right? There was a suggestion from Megha about these x, y denoting edges. That's a very interesting logic. There's a very interesting language where I don't have names for vertices, but I have names for edges. Then what will be the, so E is an edge and F is an edge and so on. And then you can talk, what will be a kind of relation that you will use? Okay, here let me use E, F, etc. What about an incidence relation, right? An incidence relation that says that E and F overlap on a vertex, right? What can you say about in this? Can you say something about, for instance, a complete graph? Think about it. What about the language of groups? Here at least I had numbers. Here I don't know what vertices to talk about. So there is no base set also to work with. What about the language of groups? What should I have in the language of groups? I need something, no? For a group.
A set and a binary operation.
Well, in the language, which set will I have?
A set of elements.
Which set?
Set of elements. Any set.
No, it's a language, right? In this language, I am using these numbers here. Here, there is no set at all because I don't know what set to write. EXY only says whatever be your graph, if X is a vertex and Y is a vertex, EXY is, binary relation on this. Same thing, there is no set in the language of groups. What I have got is this. Let me use a little circle, right? This is to talk about the operation. It's a binary, right? It's a binary operation. And then I can write things like for all X, for all Y, for all Z. Right? I can write such interesting things. What about this? Yeah.
It's not required.
It's not required, but it says it's an abelian group.
Abelian, yeah.
Yeah, I mean, like we described, if you can try to describe connectedness, why not describe abelianness, right?
Yeah.
And so on, right? But then in a group, what about anything particular? You have any particular identity? How will you write that? Yeah, how will you write it?
There exists.
X is the identity. How? Yeah.
That x dot e equal to e dot x.
Oh, you are always right. So there exists E such that x dot E equals E dot x equals, right. Well, this is an equality with, several sides, but hopefully you can write it separately, yeah. So the language of groups is very, very simple. All it has got is one binary operation, equality, quantifiers, you're in business. What about the language of rings? Well, you're going to have two.
Sir, I have a question.
Yeah.
Sir, when we are saying that the language of groups has only a binary operation and we are not defining a set on it, so what are these elements x, y, and z exactly? Because when we define the language of arithmetics, we had a natural number set and then we defined the operations that we were performing on it.
So here we had the option, if you remember, also not have the set of natural numbers, but only have 0 in it, and then have something like successor, right? So we need not have thrown in all the. These are just names that we are using for the numbers, right? 3 is a name for talking about successor of successor of successor of 0, and so on. Right? But of course there is a world of a difference, and I am glad you pointed this out, because when we say arithmetic, we have a particular mathematical structure in mind. What is that mathematical structure? The number line that we all grow up with. It's one structure. When you say groups, the whole class of groups that we have in mind, right? Class of graphs that we have in mind when we say that, right? Language of rings, we don't have any one particular mathematical structure in. There is a big difference, and this is an important difference, right? And yeah.
So just in order to define a language of groups, language for groups, for in general for all groups, we don't need the set that we are working on. We only need the binary operation that we are working on. Is that right?
Correct. Right. So in some sense, the project is this, and I think I started today's discussion with that point, that we want to describe all objects only by their properties, and those properties stated in that particular language that we have fixed. Right? So when I say group, I am interested in fixing that group by whatever properties that I can write. Then of course, can I describe that particular mathematical structure up to isomorphism in my language? Right? That is the power of language that we want to worry about. That is what all this definability nonsense is about. Yeah, it's a good point. Yeah. So, okay, so this is what it's going to be like. We're almost at the end of the time, right? So what this project is going to be, and now we are getting to the mind of somebody who had a very, very interesting project in the late 19th century. Some accent I think is missing in this. Maybe somebody knows can correct. So Frege, in the end of the 19th century, the beginning of the 20th century, took up this project to come up with one language, one mathematical language, in which you can define all these mathematical structures, right? So the project was something fabulous. Basically, it has all these. You use all this x, y, and so on. Use and or not implies quantifiers, and plug in whatever you need, right? If you want to talk about arithmetic, you plug in these. If you want to talk about groups, you plug in this binary operation. If you want to talk about graphs, you plug in one binary relation that we talked about, right? So, and this is what is called first order logic. So first order logic has the structure of some parameters that you give, those parameters will be different for different classes that you have in mind. If you had arithmetic in mind, it will have some parameters. If it is graphs that you have, you give the parameters, right? Because you want to describe groups or some particular class of groups, vector spaces, it doesn't matter. You come up with certain primitives, right? And you give it to me as parameters. What I'll do is to take that and then build logic on it using, I'll also use the symbols that we will use, and or implies not and quantifiers. And then look at, for different choices of vocabulary, what is definable and what is not definable in this, right? This is precisely the definition of first order logic. And what the Frege way of doing, which is now modernized, and what we are presenting is actually the way Tarski, another major name in logic, Alfred Tarski, defined and gave semantics to. So that's what we want to take up. So the syntax of first order logic, and but when we say first order logic, what we have in mind is not one logic, but a whole family of logical languages, right? Parameterized by, like, those function symbols that we said, like addition, multiplication, or some group action, or whatever you have. Or you might have some relation symbols like the edge relation for your this. Or if you're talking about order theory, right? Theory of lattices, what you have is only a primitive, right? Nothing else, right? You start with just a binary relation, just an order relation, and you say this order relation is, right? Because note that with quantifiers and this, you can start saying all sorts of things. Like, for instance, suppose I want to say it's a linear order. What should I say? First, I don't want it to be reflexive, so I'll say, right, not reflexive. And I have to say it's transitive for all x, for all y, for all z. X less than y and y less than z implies x less than z. And it's total. That means for all x, for all y, x equals y, or x less than y, or y less than x. Yeah, I'm in business, huh? With just these three statements, I am talking about linear orders. Look at this. For all x, for all y, x less than y implies there exists z. What does this say? Take any pair x and y, if x is less than y, it says there is something in between. So what does this mean? What kind of order is this? Dense linear order, right? Oh, already I have said it's a dense linear order. What about this? For all x, there exists y, has no endpoints, it goes on, right? What does this say? It's a dense linear order that goes infinitely far on either side. What about discreteness? Instead of saying dense, can I say discrete? Okay, whatever. My point is that in exactly 10 seconds, with just this less than symbol and quantifiers and this thing, you're talking about very interesting things, right? Okay, what about something like this? For all x, for all y, well, let me not get into this, upper bounds, etc., also. Okay, so my point is that the language of order is something that we will take very seriously and study, because this is a very simple language. I mean, it's a very minimal language and you can go very far, right? How far can you go is always an interesting question, right? Without the three dots, mind you. Three dots is always something that plagues this whole business, and but without three dots, there is no mathematics. So we do want it, right? Somehow we want to get to it. Yeah. So what we want to take up is this. What is clear is that by choosing the appropriate parameters, we can study appropriate mathematical structures. But remember, what is our objective? Of course, we want to study those structures. Shankar won't let me otherwise. But what is much more important is this internal reflection on, is this enough? Should I have more? That, so the focus, the object of study is the language itself, right? Is this language expressive enough to talk about this? Expressiveness is something that we are really interested in, but somehow we should be able to connect up statements of this kind and whatever is true or false in those mathematical structures. That connection is what we want to take up. That is the formal semantics of syntax and semantics of first order logic. I was supposed to have taken it today, but we have spent too much time on the preliminaries. Next time we'll take up the syntax and semantics of first order logic. Okay, thank you.